All right, so our next order of business is to figure out what would be the applications of these rational functions, that is, fraction functions. Functions that have asymptotes and behaviors, particularly behaviors involving infinity. What has this got to do with anything? Well, I think you'll see that it's got some good application. What we're going to do is look at two problems out of the book, like notes, something that you can follow, you can copy, and then you'll be given an assignment to answer to answer 4 questions out of the book, where you also will get a chance to just kind of figure out how asymptotes, infinity, and all that can relate to some kind of application problem. Now, the first problem that we're going to look at, as you can see from your little guided paper, is the wildlife example on page 151. It's actually number 39. Letter C is the part of the problem that we're actually going to answer. But just take a look at the problem. We've got a formula here for the number of the population of a herd of deer in a certain state game land. N stands for population. I guess it really stands for number. But we've got a numerator, we got a denominator. We're in business. Now, it might be tempting to just want to type this in your calculator, graph it, and come up with an answer. But let's kind of think about what we've learned without a calculator and how that can help us to ultimately to think about the limiting size. Now, the limiting size, you already should be thinking about a certain kind of behavior on a rational function. That is a certain type of asymptote. But I want to get you to think about the graph of this equation. Again, I know it's tempting to want to put it in a calculator, but let's kind of think about the graph without a calculator. Couple things. It's got a vertical asymptote. Now, that would be when the denominator is equal to 0. And yes, that requires some division, particularly dividing the number -1 by 0.04. Now, that really is going to look like, again, subtracting 1 and dividing by 0.04. But 0.04 is really just 4 100ths. And dividing by 4 100ths is the same as multiplying by 100 fourths. And so you end up with 100 divided by 4, a math problem that we can do without a calculator if we really needed to. Of course, it comes out to be -25. So you're going to have a vertical asymptote at -25. We can also think about some intercepts. We could think about, like, say, the y-intercept. The y-intercept's pretty easy to find. Remember, all you got to do is plug in 0. And when you plug in 0 to this equation, you find out that you really just end up with 20 times 5 over 1. Well, that's the number 100, so we get a y-intercept at 100. What else can we do? How about if we want to find the x-intercept? That would be when the numerator is equal to 0. Again, it might be tempting to want to get a calculator out, but that's only going to happen when this part of the problem is equal to 0. That's nothing more than subtracting 5 and dividing by 3. Of course, the number -3/5. So we have an x-intercept at -3/5. Now, with all of our study, we know that there's going to be a graph that passes through these points and also approaches the asymptote. Although you might be saying, well, Mr. Naylor, you left out an asymptote, and indeed I did. I left out the horizontal asymptote. Now, there is a horizontal asymptote to this problem because if you look at the degrees, they are equal. So we know that there's going to be some horizontal asymptote. In this case, using the coefficients, that A over B idea. Now, be careful because the coefficient of your numerator is really 60. And the coefficient of your denominator, well, of course, that's 0.04. Now, again, I know you'd want to get a calculator out, and you can. You can divide this on a calculator. It comes out to be 1,500. 1,500 is your horizontal asymptote. Now, we know that the graph is going to pass through these intercepts and it's going to approach the asymptotes. So we want to be thinking, well, which asymptote would represent the limiting size? And indeed, it's the asymptote that is the y value. 1,500, of course, being a y value, is limiting the actual y value of this graph. So the point behind this problem is to realize that the horizontal asymptote is what's providing our answer, that is our limiting size of 1,500 in this herd population. So as time increases, that is, as time goes to infinity, we know that the herd is going to approach 1,500. Now, a horizontal asymptote may not be the only kind of asymptote that provides a certain kind of answer. We know there's a vertical asymptote, and what I'd like to do is look at this cost-benefit problem, example 6 on page 146, as an opportunity to see how a vertical asymptote might play into an application. Take a look at this problem. It's actually worked out in the book. It's the problem about utility company burns coal, and the cost of removing the pollutants is given by this rational function. So this rational function is describing the cost to remove a percentage of pollutants. Now, as you can see, what we want to do is determine what's going to be the additional cost if our pollutants need to change from 85% removal to 90% removal. How much additional cost is there to the power company? Now, it's not really that hard of a problem. You can already see that it's worked out in the book. I'm not going to recopy the whole thing, but basically they plug in 85, and when you plug in 85 with your calculator, you can see that they got 453,000. So what would be the cost for 90% removal? Well, again, you can see in the book they plugged in 90, and there's quite a jump. Now we're up to 720,000. So a simple subtraction problem gives us the additional cost, obviously 266,000. Now, that's a pretty easy problem, but what I want to do with this problem is talk about asymptotes. So once again, we have a rational graph. It's got a vertical asymptote. It's interesting, if you think about the vertical asymptote here, which of course is at 100, what does that really mean? What does it really mean for the vertical asymptote to be at 100? Well, of course, it means that the graph is never going to get to that value, although it can approach that value. And if we think about the behavior of the graph, we already have a couple points. We have the 0.85% that goes with 453, and then we have the 0.90% that goes with 720, and we know that we have a rational graph that's going to pass through these points and, of course, approach the asymptote. So what we want to simply see here is that with the idea of a vertical asymptote, it's very evident that as percentages approach 100%, that the cost is what's going to approach infinity. In other words, it's, of course, going to be impossible to remove all the pollutants, and even if you could remove 100% of the pollutants, it would cost you an awful lot of money. So a vertical asymptote, obviously it's a value that we can't attain, but we also see it, the behavior of the graph is that the graph itself, the cost graph, is what's going to infinity. Now, there's other applications of horizontal and vertical asymptotes, and the book does a nice job of giving you some problems. That's what this assignment is meant to do, just get you guys to see a couple other scenarios. One involves a formula with area, another one involving some percentages. You'll be able to use your calculator, and I've also given you some hints as far as how to think about questions A, B, and C. Now, if it says additional question, that's a question that Mr. Naylor made up. Make sure you also answer that along with the regular book questions. Again, Part A, Part B, Part C. And then you'll be able to just upload this assignment using the upload form for today.